Okay, welcome back to Math 352. So we're up to lecture 8 now, and what we're going to be looking at in this lecture are kind of two related but different topics. We're going to first look at underdetermined systems. So in last lecture we looked at overdetermined systems. These are systems where you've got more equations than you've got unknowns. We're going to look at a similar problem, except this time we're going to look at systems that don't have enough equations. Okay, so systems like that usually have infinitely many solutions. So what we're going to do is look at finding the solution that is the smallest. Okay, so we're going to start with that, and then we're going to change tack a bit onto rank 1 updates. Okay, so let's get started. So, an underdetermined system, what does that look like? Well, basically our matrix A is this shape. So we're looking at an equation AX equals B. And what can we say about this? Well, a system like this, as we mentioned in the last lecture, typically has infinitely many solutions. Okay, unless it's not full rank, in which case it might not. Typically has infinitely many solutions. And we want to find the smallest. Okay, in particular we want to minimize the 2 norm of x. Okay, so we're just going to say that we're going to assume that A is real, m by n, and full rank. In this case, the rank has got to be m, the number of rows. Okay, so once again, we take the QR factors of our matrix. Now, our matrix is a funny shape. We often call these matrices that look like this fat. Okay, if it's got more columns than it has rows, then we can call this a fat matrix. And what we want to do, in fact, what's most useful, is to take the QR factors of A transpose. Okay, we're used to taking QR factors of matrices that have more rows than columns, so it's kind of natural that we'd take the QR factorization of A transpose. Okay, so it's the full factors. And we can write this out in terms of the components like we did earlier. Okay, the reduced Q hat, then we've got R hat with some zeros underneath. Okay, so if we do that, then A is now equal to R transpose Q transpose, which is also equal to R hat transpose Q hat transpose. Okay, now to make our life a bit easier, what we're going to do is we're going to write a new vector W to be the expansion of X in the columns of Q. Okay, so that means we write it as X is a linear combination of the columns of Q and the coefficients are W. Okay, so we can write this in pieces like we were before. So equals, well, Q is equal to Q hat and Qn, remember? And I'll write my W in 2 pieces as well of corresponding sizes, UV. So that equals Q hat U plus Qn V. Okay, so why have we done this? Well, it'll become clearer soon. So then AX equals B, which is what we're solving, remember, becomes R hat transpose Q hat transpose, that's A. X is equal to Q hat U plus Qn V, and that's all equal to B. Okay, let's just be a bit careful about this. So expanding this out a bit, we get R hat transpose Q hat transpose Q hat U plus r hat transpose q hat transpose q in v equals b. And what do we see here? Well, a couple of things. We should note q hat transpose times q. Well, hat, sorry, is just the identity. Okay, orthonormal columns, therefore that expression there is the identity. Okay, n by n. And what else can we see? Well, q hat transpose times qn. Every column of q hat is orthogonal to every column of qn, so that there is just 0. So our equation reduces down to r hat transpose I u plus 0 equals b. Okay, this can be solved efficiently for b, sorry, for u, by forward substitution. Okay, just like back substitution, except r transpose is lower triangular, so you start at the top instead of at the bottom. Okay, so that determines what u must be. Okay, so we've got no choice. U has to be that. Okay, as for v, okay, we're just going to note that the 2 norm of x, remember that's the thing we're trying to make as small as we can, is the same as the 2 norm of qx. Okay, as we've discussed earlier, if you multiply a vector by an orthogonal matrix, its length doesn't change. So that equals the 2 norm of our vector w, which equals the norm of u squared plus the norm of v squared. Okay? However, we've got no constraints on what v must be. Remember, this is our equation here that expresses ax equals b. And what we found was that v just vanished. We don't actually have any constraints on what v should be at all. U is specified by r hat inverse transpose b, and v is not constrained by anything. Okay, so to minimize the 2 norm of x, all we do is set v equal to 0. To minimize the 2 norm of x. Okay, I can keep putting the squares in, but it's actually the same problem. Okay, so just looking at this equation here, the length of x is equal to the length squared of u plus the length squared of v. U we have no choice about. V we have complete choice, so to minimize that, we just set it equal to 0. Okay, so once we've done that, we're basically done. So putting it all together, then x equals q hat u plus qn v, but we've set v equal to 0, so just equals q hat u, and we said that u is given by r hat inverse transpose b, and finally, so that gives us our x, and the length is just equal to the norm of u squared, which equals squared. Okay, so once again, if all we are interested in is the solution, all we have to do is compute the reduced QR. So just to sum up, all we need to do is compute the reduced QR factors of A transpose, don't forget to use A transpose, then X equals Q hat R hat inverse transpose B. In the second part of this lecture, we're going to change tack a bit, and we're going to start talking about rank 1 updates. Now, you probably haven't heard of these before, so before we get started, I should tell you what they are. So, a rank 1 update. A pencil. What is a rank 1 update? Well, if we take a matrix A, and we add to it a rank 1 matrix. Now remember, we can always write a rank 1 matrix as an outer product of two vectors, like that. Then we call the matrix that we get as a result a rank 1 update of the matrix A. Okay, so we'll say A plus, which is what we'll call them in this lecture, is a rank 1 update of A. Okay, so you can imagine doing one of these updates. So things that you can do, for example, with the rank 1 update, and we'll look at that soon, is you can replace a row or a column of your matrix A, for example, by an update of this kind of form. So you can imagine, for example, if you're solving a least squares problem, and you wanted to change one of the data rows, for example, that you might want to do that. And if you've got a full QR factorization, it might be that you don't really want to expend the effort in computing the whole thing again. You want to do something a bit more cheaper. So some quantities can be recomputed, or recomputed hang on, that's probably not the best way of saying that. Some quantities can be updated easily or efficiently. For example, we can update A inverse. If we already know A inverse and we do a rank 1 update to A, then we can easily update A inverse as well. I'll show you how to do that soon. And that's one example. The QR factorization of A. Okay, if we do a rank 1 update to A, we can also fairly cheaply update the QR factorization without having to recompute the whole thing. Okay, so those are the two things we're going to look at in this part of the lecture. So we'll start with the rank 1 update to A inverse. Okay, so basically this is a special case of a formula that has a few names, but we'll call it the Sherman-Morrison-Woodbury formula. Okay, published by a few people pretty much at similar times. Okay, let's call it the SMW formula. And that is given by the following expression. Okay, is equal to A plus U V transpose inverse, which in turn is just equal to A inverse minus the following nasty. A inverse U V transpose A inverse over 1 plus V transpose A inverse U. Okay, now I'm going to get you to verify this as a tutorial exercise, so I'm not going to go into any more detail on that formula right now, but that's basically the formula we use. Now, at first glance, it looks like quite a messy, complex thing to work out, but it's actually not quite so bad as it looks. Okay? So, the way we do this is we take our formula, these two terms here, remember we already have A inverse, so these two formulas here are just matrix times vector. Okay, so we compute those first, and then we just have a vector-vector product, which is cheap, divided by also another vector-vector product here. Okay, so when we actually compute this thing, we work out the red circled pieces first, and then we combine it all together. So the most efficient way is to compute A inverse U and V transpose A inverse first, as both are order n squared operations. Now what do I mean by that? Okay, so I'm introducing some terminology here that we haven't really looked at before. When I say that computing A inverse U is order n squared, that means about n squared multiplications and additions need to be computed. Okay, so every time you do a row of a matrix times a vector, then that costs you about n, or maybe 2n. Multiplications and additions individually, you can work this out for yourself if you like. So if we do a matrix times a vector, we have to do that n times. So we have about order n squared operations. Okay, so so if we do that, then calculating the overall update is also order n squared. That just means a constant multiple of n squared. Update is therefore order n squared as well. Whereas to recompute A inverse takes n cubed operations. Okay, so I may cover this in more detail a bit later on in the course, or I may not. But basically, to compute an inverse, which is what you have to do whenever you solve a system of equations from scratch, it takes you order n cubed operations. So to do your Gaussian elimination, it takes you order n cubed operations. But if we already know A inverse, and we know that's just a rank 1 update, we can do the overall update in order n squared operations, which is a big difference. Okay, you can compare these two things. So order n cubed, as n gets big, so if n goes from 100 to 1000, then it's going to take 1000 times longer, 10 cubed times longer. Okay, but if n goes from 100 to 1000 for an order n squared operation, then n goes from then the operation overall will only take 100 times more, 10 squared times more. Okay, we'll look at some examples about how you might use this. So an example. Okay, so the rank 1 update, rank 1, A goes to A plus B minus AJ EJ transpose. What does that do? That replaces the jth column AJ of A by B. Okay, how does that work? Well, look at this. B minus AJ EJ transpose equals B EJ transpose minus AJ EJ transpose. Okay, equals B times 0, 0, 1, dot, 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 0, whatever, minus AJ times the same thing, which equals 0, 0, B minus AJ, 0, 0, 0. Okay, so when we add that matrix onto A, then we subtract off the jth column and we add on B, and we've replaced the column. Okay, you can come up with a very similar expression for replacing the row of a matrix. Okay, so that's an example of the type of operation you can do with a rank 1 update. Another example. Solving two sets of linear equations. Okay, so let's say we want to solve these two equations here. Ax equals b. We want to solve that. And we want to solve a plus uv transpose x tilde. I was good to give it a different name. X tilde equals b as well. Okay, so how do we do that? Well, applying the formula, we'll apply the Sherman-Morrison-Woodbury formula to compute our x tilde. So, in this context, by the way, x tilde is called a rank 1 update of x. Okay, so we get that x tilde equals A plus u v transpose inverse b. Okay, we're just going to basically apply the Sherman-Morrison-Woodbury formula here, so let's just give myself some more space, equals that horrible thing. Just write it slightly differently from before, but it's the same thing. 1 plus v transpose A inverse u, A inverse u, v transpose A inverse all times b. Okay, now looking at that, when we expand this thing out, we're going to get a couple of A inverse b terms in here, which is just x, isn't it? So A inverse b, the first term is going to be x, minus, well, we're going to get a v transpose A inverse b, which is a v transpose x, which is just a scalar, so I'm going to write that down first. Don't forget you can move scalars around to the outside of matrix multiplication expressions. So I can stick that there, and on the bottom I'm going to have 1 plus v transpose A inverse u, and I still need to take into account this A inverse u term here, so it's going to be an A inverse u as well. Okay, so what have we got there? Well, looking at the various pieces, we can just do an inner product of v transpose times x, that's easy. A inverse u, okay, we're going to need to compute that thing. So we can solve both systems. Just get some more space again. Okay, we can solve both systems by basically factoring A. Okay, when I say factoring A, once again, it's something that we haven't really looked at in detail in this course. So when you do Gaussian elimination, you're basically computing, just as an aside here, so yes, when you're solving Ax equals b by Gaussian elimination, that remember we from second year, you're basically turning your matrix A into the product of a lower and an upper triangular. So LUX equals B. So we then, just to remember, let Z equal UX. Then we solve. What do we solve? We solve LZ equals B by forward substitution. And then we solve UX equals Z by back substitution. So like I said, it's not this type of thing I'm majoring on in this course, so I'm just going to touch on it briefly. But basically this step here, factorising A, is an order n cubed operation. Okay, that's the hard bit. Doing the Gaussian elimination is the hard bit. Doing backwards or forward substitution costs only order n squared operations. Okay, so the cost of Gaussian elimination is dominated by the cost of computing the LU decomposition, which is what you're doing when you're doing Gaussian elimination. Okay, once you've computed the LU factorization, then you can solve for different right-hand sides by just changing B here, and you've only got order n squared things to do. So, we can solve both systems, going back to our problem, we can solve both of these systems by factoring A equals LU, then computing X equals A inverse B. So that's just doing those the forward and then backward substitutions, order n squared. So that one there is order n cubed. Just make some more space here. You can move across. Ah, what a mess. Let's just tidy this up. Sorry about that. That step costs order n cubed. Computing X equals A inverse B. We'll stick to the colour scheme as well, which is order n squared. And then computing W equals A inverse U, which, given we've already factorised A, is also order n squared. And then using our W in this formula here, and then computing X tilde equals X minus V transpose X over 1 plus V transpose W all times W. Okay, and each of the terms in here are just order n. Okay, so the cost of doing this is only an extra order n squared. So it costs really no more than it would have anyway, because the cost of solving a system of equations is dominated by the LU factorization, by Gaussian elimination, which is an order n cubed thing. Okay, we might come back to this a bit later on in the course, this kind of idea of how much various things cost. But for now, we'll just sort of leave it at that. So if I mention things being order n squared or order n cubed, that's basically what I'm talking about. But like I said, I may do it properly a little later on. Okay, so that's the rank 1 update of basically the inverse and how you can use that. Another thing that we quite often want to do, and can do quite efficiently, is a rank 1 update of QR factorization. Of QR factors. Okay, so this bit can be a little bit involved, so let's get cracking. So we'll just set it up. We'll say A equals QR, and once again let A plus equal A, be a rank 1 update of A plus UV transpose, and we know that that's equal to QR plus UV transpose. Okay, now I'm just going to rearrange this slightly to make life a bit easier. Rearrange. Basically, I'm going to put the orthogonal part on the left. So we'll get Q transpose A plus, no, subscript plus, equals R plus W V transpose, where W equals Q transpose U. Okay, now what we're aiming for is A plus equals Q plus R plus. That's where we want to go. We want to find out what Q plus and R plus are for our rank 1 updated A. Okay, now basically I'm going to do something here which will appear to be pretty unmotivated, but once you see it done, you'll hopefully understand why I did it. So what we do is we use Givens rotations starting from the bottom to make all but the first two elements of W0. Okay, so if we take our W, which at the moment is just a vector of some sort, then we start at the bottom and we use the bottom two entries to rotate a 0 into the bottom position. And then we do the same thing again. Just move that across, make some more room. Okay, then we do the same thing again, using the next two as our vector, to rotate a 0 into the second to bottom position. And we keep doing that, basically until we get to introducing a 0 into the third position. Okay, so I've just done a number of Givens rotations on my vector W to get it into this format here. Okay, now we don't yet know why I've done that, but we'll see in a second. Okay, so if we do this, then the product of the G's of the Givens matrix of G's with W V transpose has the following form. Okay, G23. Tell you what, I just need a bit more space here. I'm just going to move this across to here. I'll draw a line here, and let's give us a bit more working space. The product of the G's with WV transpose is equal to something that looks like this. G23, G34, etc., Gm minus 1m, WV transpose is a matrix that has non-zeros up here, okay, and zeros everywhere else. Okay, you can think about that just if you multiply any vector V transpose by a vector of this form, then that's the kind of shape you get. Okay, what do these matrices do to R? What do these matrices do to R? Turn R into what we call an upper Hessenberg. There's a new term for you. Matrix. Okay, so I'll show you what that means. So this is basically zeros beneath first subdiagonal. Okay, so an upper Hessenberg matrix is like an upper triangular one, except that you can have entries on one diagonal below the main one. So just for a moment, I'll work with 4x4s just because it's kind of a bit clearer. What we have is that G G34 times R, what does that look like? Well, so we're going to have a givens matrix. And the 3, 4, 1 looks like this. R, to start with, looks like this. And we're basically rotating the bottom two rows. So looking at that, the worst that can happen in terms of introducing non-zero elements is that we introduce an element in this position here. Okay, so that's going to look much the same, except that it will introduce one extra non-zero just here. Because we're just rotating those bottom two rows, then the worst we can do to our matrix in terms of its structure is to introduce a non-zero here. Okay, the next thing, so that's G34, that's R, that's G34R. The next thing we do to it is we multiply by G23. Okay, then multiply by G23. Okay, so we have G23, which looks like this, times G34R, which looks like this, upper triangle, but at the moment we've got that one extra entry in it. And now we're just rotating rows 2 and 3. So you can see that in terms of introducing extra non-zero entries, the only place we're going to get a new one is here. So its structure is going to be like this. Fourth row gets left alone. So we're basically introducing these new elements in here, just on diagonal underneath the first one. Okay, so if we were to keep going, which we don't need to, because if you just look up here, we stop at G23, we're just introducing an element beneath the first diagonal each time. Okay, so we just need to kind of put all this together. So why have we done all this stuff? Well, let's see if we can combine it together into one kind of formula here. I'm trusting you've written this down somewhere because I'm going to get a blank page. If you haven't done that, then that might be a good time to do that. Putting this together. What we're going to do is we're going to multiply both. Remember we had to start with, we had A plus Q transpose A plus equals R plus W B transpose. In fact, okay, that's where we started. And we came up with a sequence that turned this right hand side into a matrix with 2 rows at the top only, and the rest zeros. So if we apply all these matrices in turn, so for our 4x4 case it looks like this: G23, G34, Q transpose A plus. I'm just applying that sequence of orthogonal transformations to both sides of my equation, equals G23, G34, R, plus, what else? G23, G34, WV transpose. Okay, and let's look at the shapes. So we did this one. That's our upper Hessenberg matrix, which has some extra entries beneath the first subdiagonal. And this one here looks like this. And the rest is zeros, just as we did before. So that equals another matrix, which is still in upper Hessenberg form. Okay, now we've gone and added an extra one in here. Okay, so I'll draw a dashed line down here. And we'll call that matrix H. Okay, so when we apply these transformations, then we've mucked up the right hand side a bit. It's no longer upper triangular, but it's actually close. It's the so-called upper Hessenberg matrix. Okay, H is Okay, so now we're on the home stretch. So now what we do is we apply another sequence of Givens rotations, this time starting from the top, to rotate out these extra entries. Okay, we now apply another sequence of Givens rotations. Okay, so we'll start with the top, 1, 2 prime, I'll call it, just to distinguish it from the other ones. G, 2, 3 prime, up to G, M minus 1, M prime, to rotate out the subdiagonal entries. Okay, so now we're just basically doing steps that we did in our Givens QR factorization. Okay, and most of it we can ignore because most of it's zeros. Okay, so what do we get finally? So scroll that down a wee bit. So finally, we get a big nasty looking expression, but it's not quite as bad as it looks. So once we've done this, we get this big thing here, G prime, some dots. Okay, there's my sequence of Givens ones that I just told you about. Then we'll stick back in the original sequence. Okay, so we're just applying this to the equation again. Times Q transpose A plus, okay, which incidentally is what we're wanting on the left there, equals G M minus 1 M prime through to G 1 2 prime. Sorry, that should be a 2 over here. H. Okay, so we've done this big array of Givens transformations. It looks like a real mess, but if you look carefully, the number of rotations applied to an orthogonal matrix, that there is just the orthogonal matrix Q plus that we're after. Well, the transpose of it anyway. Okay, and there's A plus equals, and we've just fixed this thing here to make it upper triangular. So that's the R plus we want. Okay, and we're done. So we've basically applied 2m minus 3 Givens rotations, and that has given us our new QR factors. So each Givens rotation takes only order n operations. Okay, as it only affects 2 rows at a time. Okay, so that's good. Therefore, the QR update takes order m times n operations. Okay, because we have to do 2m minus 3 of them. Rotations are required. Okay, and so of course if m equals n, then it's order m squared. So once again, the update is only order m squared, whereas to compute a QR in full, computing a full QR is order n cubed. Takes order m cubed steps, operations. Okay, so once again, updating our QR factors is much cheaper than recomputing the QR factorization from scratch. Okay, so in the last part of this lecture, I'm going to try and do this in MATLAB. So we're going to take a bit of a break from the theory. We're going to see if we can put together what we've basically done in this lecture into some code. So disclaimer, I'm starting from a blank slate, and I'm going to see if I can sort of work this thing out from scratch. Okay, so part of why I'm doing this is so that you can get a bit of a feel for what it's like, once you're a bit more used to it, to develop MATLAB code and the kinds of things you'll need to do. Okay, so I'm wanting to write a function that takes in, I'll call it my QR update, it takes in QR factors of a matrix and also takes in the rank 1 update vectors u and v. And what's it going to return? It needs to return my updated QR factors, q plus and r plus. Okay, so that's the basic shape that my function should take. And I'll just put in this bit here. Okay, so notice we don't need to pass the matrix A in at all, because A is being passed in the form of its QR factors. Okay, so what we need to do is just figure out what we need to do. So I'll just switch to a good directory, and I'll save that. My QR updates, that's good. Don't forget, when you're writing MATLAB code, and you're writing a function like this, you need to make sure that the function has the same name as the file, otherwise MATLAB's going to get confused. Also, don't call it something that already exists, like QR. Okay, so if we look back to our lecture, what was the first thing we had to do? Well, let's see. The first thing we had to do was to compute. We were looking for a sequence of givens rotations that made this W vector take this shape here. Okay, so we need to know what W is. W is given by Q transpose times U. So let's just start by doing that. So W is equal to Q transpose times U. Done. Now first, we want to apply a sequence of givens rotations to make W only 2 non-zero entries. Okay, so how many of these things do I have to do? That might be the first thing to think about. Well, let's see. We need to go from 2 up to m minus 1. So that sounds like m minus 2 of these rotations we have to do. So I'm going to go for I equals 1 to m minus 2. I'm going to do these in a loop, and I'm going to define what these givens rotations need to be as I go. So I'm going to start with W, and I'm going to rotate it using givens rotations. So we start at the bottom, do we not? Yep, we apply g m minus 1 m first. So what I might even do, what might be slightly nicer, is if I start I at m minus 1, and I go down to 2. That might be even nicer, because that way I don't get confused about what indexes I need to use. So I need to work out my givens matrix, which is going to be a plane rotation, and it's going to be a plane rotation of the last, well, it's going to be entry I to I plus 1 of my vector W. Okay, and we're going to work out, what are we going to have to work out? Well, we're going to have to work out W is going to have to be G. We're only going to look at the last 2 entries. It's going to be rotated by that matrix G. Okay, so hopefully that works. I have no idea if that works, but we should probably check. Okay, so what I'm going to do is I'm going to test my code. So with a bit of luck, that will just work. But I'm not convinced, so I want to actually see this happening. So I'm going to leave my semicolon off here, and I'm going to try it on some code. So I'll define a matrix A, make it 5 by 5, and I'll get the QR factors using MATLAB's QR. Okay, and I'll define some random u's and v's. Now I'm going to test my code by calling my QR update of Q, R, U, and V, and see what happens. Undefined function or variable m. Okay, so first thing I have to do, which I haven't done yet, is decide what size we've got. So it's going to be the number of rows, for example, in Q. That will do. So I'll try again. Nothing happened. Okay, so why did nothing happen? Nothing happened because I forgot to say that my loop needs to be stepping down in increments of -1. So I'll try it again. And now we've got a problem that the index exceeds the matrix dimensions. So I'm just missing a times here. I don't know why I did that this time. Here we go. So if we look at the output, has it done what we wanted? So I'm basically getting it to display W at each step. So after the first one, it's introduced a 0 here. Second one's introduced a 0 here. Third one's introduced a 0 here. And then we've stopped because that's where we want it to stop. So at that point, I'm actually happy that my code works as I want it to, and I'm going to move on. Okay, so that's quite cool. So I'm happy about that. I don't want to see these things every time I do it, so we'll stop there. Okay, so I've basically worked out my sequence of givens rotations that I needed to start with. But if we go back to our lecture notes, we need to do a bit more than that. We also need to apply these givens. Where's my overall formula? We also need to apply these rotations to our matrix R to give us that matrix H. Here's my formula for that. Here, so you notice I need to apply these to R as well as applying them to WV transpose. So that will give us our matrix H. So let's do them to R as well. Give it to MATLAB, back to MATLAB. So we've got our G defined already. So I'm just going to multiply my R matrix. So I'm going to look at rows I through to I plus 1, all columns. Not going to touch the rest of it. Equals G times R of I to I plus 1, all columns. Okay, so I'm just going to run that as well. And there's a mistake. Mistake is what? Who can see it? Didn't like that. I must use a semicolon instead of a colon by accident. Try again. Okay, and after these rotations, you can see after we do one rotation, R has picked up that extra non-zero entry there. After I do the next one, it's picked up that non-zero entry here, and the last one introduced that non-zero entry into that position. So we're getting that kind of form here that we expected. Now we need to add that to WV transpose to get our matrix H. So H equals R plus W times V transpose. Once again, I'll run my code, and here's my upper Hessenberg H. So that worked. Okay, notice what I'm doing. I'm not trying to write my whole code in one hit. I have no idea if it will work if I do that. I'm sort of looking at my output at each step of the way just to see if it's working properly. Okay, so I'm actually quite confident this is fine because I've got the right form that I wanted, and I'm happy that I can move on now. Now the next thing we had to do is we had to basically apply givens rotations starting from here and moving down to get rid of those entries at the bottom there. So we started with our G12, so I'm going to start my I at 1, and the last one I do is Gm minus 1. So now I'm going to define some givens rotations again, and now I just need to be careful about what I'm rotating. So it's going to be my upper Hessenberg matrix, it's going to be column I, and it's going to be rows I through to I plus 1, I think. Okay, so the first, just sanity check, first step, I is 1, so it's going to be rows 1 to 2, column 1. Next time it's going to be rows 2 to 3, column 2, and etc. So that's good. So I think that's going to work. And I must apply my rotation to my matrix H. So H of rows I through to I plus 1, all columns, is equal to G times H of I through to I plus 1, all columns. Okay, so hopefully by the end of this, my H should now be upper triangular. So, is it? I'll put this step on here so I can actually see the output as well. Run that again. So, now we've got, it started as Hessenberg, and now we're rotating to get rid of these subdiagonals. So after one rotation we've got rid of this one, that's good. After another one we've got rid of this entry, it's gone to 0. This one's gone to 0. And then this one's gone to 0. So it looks like everything's just fine. And finally I'm displaying my H, which is upper triangular as we hoped. So I'm pretty confident that my R plus, or that's my H, is right. Now, we're actually returning RP, so I'm just going to go through here and rename all my H's into RP, because hey, that's what we want to return anyway. There's one more there. And I'm happy that my sequence is working. Okay, so I'm basically done in a sense, in that I've worked out my R plus. The other thing I need to do is work out Q plus. So if we look back at our notes again, what is Q plus? Well, Q plus is basically all of those givens rotations applied to the matrix Q transpose, and then I take the transpose of that at the end. Okay, so we can actually just plug those in. So QP is going to start off being equal to Q transpose, and I'm basically going to go through and apply these givens rotations to QP as well as to everywhere else I'm applying it. G times QP of I plus 1. Okay, and I'm also defining the givens rotations here, so I should put in a similar line here. Okay, notice what I'm not doing. I'm not storing the G's individually. I'm computing them, I'm applying them to the various pieces they need to be applied to, which is, in this case, RP and QP, and then I'm letting it go, because we can get a new one next time. So hopefully, the last thing I have to do is QP has to be the transpose. Okay, if we apply those rotations we get QP or Q plus transposed, so I just need to take the transpose at the end. So with a bit of luck, I'm now all good. So, what's the acid test? We call it QP RP equals my QR update of Q, R, U, and V. Must not forget my closing bracket. Okay, so first thing, is QP orthogonal? Well, if it is, then that there should be the identity. And it is, so that's good. Second sanity check, is R upper triangular? Yes, it is. Okay, so I've got an orthogonal matrix and an upper triangular matrix. So if we multiply those together, we should hopefully get our rank 1 update of A. So, is that equal to A plus U times V transpose is the big question, and thank goodness for that, it is. Okay, don't be put off by all these numbers here. These are all multiplied by 10 to the negative 15, so they're all virtually 0. Okay, so we're done. So I have, in about, I don't know, how long will that take? About 10-15 minutes, done the QR update code. So what I'll do is I'll put this code on Learn with a publishable M file to go with it, so you can have a bit of a play around with that as well. That should also help you with your class file, with your QR factorisation that you've done earlier. Okay, so that's me. That's the end of our lecture. So have a good weekend. I'll see you.